All right, so we talk about Bitcoin specifications and structure of the Bitcoin blocks. So now it is a good time to talk about wallets. So let's recall the main misconception. People always say that digital wallets are physical analog. So they say that physical wallets have three main purposes. They store cash. When you want to pay for something, you remove cash from it, or you can add more cash to it when you receive it. So a physical wallet have three main purposes. So many books, blogs, web pages claim that digital wallets are digital analog of physical wallets and are used to store cryptocurrency, send cryptocurrency, and receive cryptocurrency. But the thing is that digital wallets do not store cryptocurrency. Okay, this is very, very important. I mentioned it before, but I want to mention it again. Many forensic investigators think that the cryptocurrency is stored on the wallets. So whenever they capture a laptop and the person, owner of the laptop admits that there is a wallet software and there are some cryptocurrency in it, some forensic investigators think that since the laptop is turned off and not connected to the internet, nobody can withdraw that money. Okay, but the money, again, the cryptocurrency is not in the wallet, it is on the blockchain. So anybody knowing the private key can transfer the ownership of it. Okay, so this is very, very important, a concept that most people still don't understand. So with some blockchain networks, users must manage and securely store their own private keys. Okay, so Bitcoin is an example of that blockchain network. Okay, because users must manage and securely store their own private keys. They often use software to securely store them. There are many software. This software is often referred to as a wallet. The wallet can store private public keys and associated addresses. It may also perform other functions such as calculating the total number of digital assets a user may have. Your wallet check if you received a payment by looking at the blockchain and analyzing all of the addresses you have the private key for and provide the total balance. So this is why your wallet software tells you you have this amount of Bitcoin. Like the way I looked at the Genesis block and checked the wallet address and told you that this wallet address actually has 68 dot something Bitcoins, but actually it doesn't have that amount in a single transaction. As we had seen, that wallet address received that money in more than 3,000 transactions. Okay, so actually the blockchain only stores those transactions, but the wallet software checks all of them and gives you the total at the end to you. Okay, so whenever you want to spend some of it, the wallet software also manages it. For instance, if you want to spend 20 of them, it checks some of the transactions so that their total exceeds that 20, and then you can create a transaction and use it. So if a user loses a private key, then any digital asset associated with that key is lost, because it is computationally infeasible to regenerate the same private key. Recall that you have to solve the discrete logarithm problem. In the case of Bitcoin, you have to solve the elliptic curve discrete logarithm problem, which is very, very hard to solve. So if you lost the private key, then everything is lost. This is why, some people, most of the time when you use a wallet software, it creates the private key and stores in a file. But this is not a good idea, because if a virus or a Trojan infects your computer, they can take that file, and this way they obtain your private key. For this reason, most of the wallet software asks you a password, and you enter your password. So using your password, actually they use a hash function thousands of times, taking the hash of your password thousands of times, and provide the SHA-256 output, and use that as an AES key to encrypt your elliptic curve private key. Okay, so whenever you want to send Bitcoins, you have to rewrite your password. The software will regenerate your AES key. It will decrypt your private key and sign the transaction. So this is how the wallets work actually. Okay, so if you forget the password, then everything is lost. If your computer is destroyed, your private key is lost again. So it goes again. So whenever you kind of encrypt your private key by putting a password, there they use password-based key derivation function. So at the end, since it is encrypted, maybe you can take the copy of your encrypted private key and store it someplace else. So it is always a good idea to, remove single point of failures, because if you keep it on a single laptop, your hard disk might be broken and everything might be lost. So we believe that a lot of Bitcoin is now lost because a lot of people maybe forgot their passwords, maybe lost their private key files. And so for this reason, we cannot spend most of the previous Bitcoin transactions. Okay, so I also want to talk about the misconception. When people talk about NFT, I looked at the Wikipedia because I realized that a lot of people are using this sentence, and I realized that they are taking it from the Wikipedia. And in Wikipedia, it says the following sentence: while all Bitcoins are equal, each NFT may represent a different underlying asset and thus may have a different value. So here they're trying to tell why NFT is something different than a cryptocurrency. Okay, NFT is different than a cryptocurrency, I agree, but saying that all Bitcoins are equal is kind of a wrong, okay? And let me tell you why it is wrong by giving you an example. So think about Turkish coins, okay? 1 Turkish lira actually started to be built in 2009. 1 year ago, we had new Turkish lira, but in 2009, starting from 1 January, very similar to Bitcoin blockchain, at that date, we started the 1 Turkish liras in coin, okay? And today, we still have 1 Turkish liras. They are still minted in 2022. So you might say that, okay, 1 Turkish lira from 2009 and 1 Turkish lira from 2022 are the same because they have the same value. But the thing is that some collector might give you more than 1 lira to buy your 1 Turkish lira coin from 2009, because on it, it says 2009, because it is the year it was minted, okay? So the similar thing happens in Bitcoin. For instance, Satoshi's 50 Bitcoins in the Genesis block belongs to the, initial block. So it is minted in 2009, okay? So anything mined today is mined in 2022, right? So, okay, in theory, they are the same, but some people might prefer, like a collector, might want to buy a Bitcoin that was mined in 2010. Okay, that is what I'm trying to say. So with this idea, older Bitcoins might be preferable by some. For example, think about this. Consider a Bitcoin conference where early adopters receive 20% fee reduction when they pay with Bitcoins that were mined before 2011. This can happen because since we can look at the blockchain, we can see which money transferred at which years, at which blocks, and so on. We can go back to the initial coin-based transaction where it was mined. So we can see which Bitcoin is mined at which year. Okay, some of them are older, and some people, some collectors prefer to have them. So saying a sentence like all Bitcoins are equal, kind of a wrong to me, okay? Because they are not. For example, you can simply write a code which older Bitcoins will be more profitable than the newer ones and so on, okay? And you can actually create many different games, you can generate many different software where old Bitcoins can be used and new Bitcoins cannot be used and so on, okay? But anyway, this is some share. Okay, so let's talk about wallet addresses. So let's recall that we talked about pay to public key hash transactions. But in order to pay to them, we actually talk about public key hash, right? We said that we generate wallet addresses as follows. You take a point on this elliptic curve, okay? So this is actually generated when you choose a private key. You add the base point on the elliptic curve d many times. D is your private key, and at the end you obtain a point on the curve and we call it K. So this is your public key. So it's 256 with X and Y coordinates, result in 512-bit value. So you take the SHA-256 of this, then RIPE-MD 160 of it. So result is just 160 bits, which is 20 bytes. But we encode it with base 58, okay? 58 means that this encoding has 58 characters, okay? So recall that how we did the encoding. We add a prefix to the data called the version byte. So compute the double SHA-256 of prefix and the data. The first 4 bytes of the double hash called checksum is appended to the prefix concatenated with data. So the result prefix data checksum is encoded using the base 58 alphabet. So we gave an example like this. So base 58 alphabet is this. As I already mentioned before, some characters and numbers are removed to avoid confusion. For instance, 0 is not included because it looks like the letter O. Similarly, capital O is not included here, okay? So assume that I chose my hash output, so I go back. I take an point on the elliptic curve. Assume that when I take the SHA of it and then RIPE-MD of it and obtain A, and for some reason I was lucky and it was something in this form, 0, 1, 2, 3 to F and so on, okay? So 20 bytes. So base 58 encoding is performed like this. You concatenate the version of it, 0 in this case. So you put a byte with zeros. You take double SHA-256 of this. The result is this. Then you take the first 4 bytes. This is your checksum. Then take the checksum, put it to the end of this part, and represent it with base 58. Since the beginning is 0, this part, once you perform the base 58 encoding, it starts with 1. So this is why basic Bitcoin wallet addresses starts with 1, okay? So question is, can I have something here that looks like a word? Okay, I will give examples in a minute. But in order to check this, you can use online calculators. Like there's a good tool I found that's, calculates base 58. And if you want to check if your SHA-256 calculations are correct, you can use this online calculator. Of course, you can use your operating system to perform SHA-256 operations, but most of the time those functions take the input as characters, but here maybe you want to put them in hexadecimal notation. In all of these slides, I use the hexadecimal notation, but the executables would think that your input is in characters and bytes, okay? So this is why sometimes online tools are useful. Okay, so to answer my question, we can have vanity addresses. There are something called as vanity addresses. These are Bitcoin addresses that contain human readable messages. So let's look at a block. This is from block 666,666. Okay, there is a transaction here, as you can see from the BC1 address, which we haven't talked yet. But to the two accounts, which one, all of them starts with 1, which is unavoidable. But here there is a word God and there's a word Bible. So it looks like a coincidence, but if it were only God, we would think that it is a coincidence because it's just 3 letters. It could happen. But now Bible has 5 letters. So, and they are together. It looks like this is not a coincidence, right? And actually, if you look at the block number, you will realize that there are too many 6s here. Actually, 666 is a number referred in the Bible, which is actually referred to as the number of the beast. Okay, so this is a deliberate message. So this transaction probably created before and waited for this block to happen so that the owner sends this amount of money to accounts that start with God and Bible. And actually, if you look at this transaction, you will realize that there is a hidden message there, actually apart from the Bible, which I will show you in the transactions session, okay? So you can have similar things. Vanity addresses require generating and testing billions of candidate private keys until a Bitcoin address with the desired pattern is found. So in order to have something that starts with God, you took a private key, calculate the public key, calculate the base 58, look at it if it starts with God. If not, take another private key and do the same thing again and again. Since it is 3 characters, it is not that hard. But when it is longer, it becomes harder. So let's look at this example from this blog. So it says, verify HN post fake. So this is actually, then we realized that this is created by the people from WikiLeaks, because there was a post in HN saying that the founder of WikiLeaks was dead. So here they're actually saying that that post is fake, but instead of saying it, they just put it on the blockchain. Okay, so as you can see, there are 4-letter or 5-letter characters here. So you might ask that, couldn't they write it on the one wallet address, right? You could also write word fine here, right? But it becomes harder to generate those addresses. So let's see how hard it is. So if you want your first character to be something that you prefer, actually, since the one character can take 58 different values in this base 58 encoding, actually you need to make 58 trials at most, with the expected value. So this, I calculated also the powers as 2 to show that how much is within our computational power. So if you want specific 2 characters in your wallet address, you have to perform small amount of operations. This can still be done in a second, I guess. But once the character size increases, the number of trials you need to perform increases too. So currently we say that, performing 2 to the 8 operations, is not easy for us, but maybe secret agencies can done. So having 13 or 14 character addresses is still possible, but it might take years, and it wouldn't be profitable. If you have that much amount of computational power, you wouldn't waste it for this kind of calculation. So this kind of 1 to 6 characters is maybe a lot easier to achieve. So if your first name is shorter than 6 characters, you can have a Bitcoin address with your name as the first 5 or 4 characters, right? Okay. Of course, if your the characters in your name included in base 58, okay, because some characters are removed. But it will be cool to have your name as your Bitcoin wallet address, so you can do it. Okay. So we talked before, the version prefix, when I calculated in the previous slide, I put 0 because this is for public keys. But if you're going to create a base 58 encoding for pay-to-script hash address, you have to put 05 in hexadecimal. But once you perform the base 58 encoding, the result will be 3. This is why basic addresses start with 1, pay-to-script hash addresses start with 3. Okay, so since most of the pay-to-script hash addresses are multi-signature transactions, people looking at them kind of understand that there's something different going on there. But with the addition of Schnorr signatures, now we can aggregate keys. So our multi-signatures will still look like 1 addresses. So this is why it provides some kind of anonymity. Okay. So people seeing those addresses will think that it belongs to a single person, but maybe n people signed it and so on. So for the private keys, this is for storing your private keys. There is a format called WIF. So if you want to encode your private key, you put 80 to the beginning. So a private key starts with 5K or L. This is important because if you're a forensics investigator, you should know what a private key looks like when it is encoded. Okay. So the 4 bytes of the double SHA-256 is used to detect errors. I mentioned this before. Error detection prevents sending Bitcoins to invalid addresses. If an error occurs on the base 58 representation, when the error corresponds to the checksum, we always detect the error, because since there's an error in the checksum, when you calculated the checksum again, they wouldn't match. But if happens in the public key hash part, then we detect the error with probability 1 minus 1 over 2 to the 32, which is very close to 1. So most of the time we detect it. So it is not much of a problem. But the important thing is that with the pay-to-script hash address, those with starting with 3, there is no checking mechanism. So if you write, misspell something, then that money is lost. I told before, I know a few cases where some people contacted me and tell that they transferred Bitcoins to a 3 address, more than 1 Bitcoins, but they mistyped a letter. And I told them it is lost. You cannot withdraw it again, okay? Because you actually transferred it to a script of hash, which you don't know. So if you can come up with a script that will give you that hash, then you could withdraw it, but it is not that easy, okay? So this is why it is lost. It is similar to the solving discrete logarithm problem, okay? So okay, let me continue with the script hash. So traditional Bitcoin addresses begin with the number 1, but we briefly mentioned what pay-to-script hash, how the script hash works. Anyone can send Bitcoin to one address, but that Bitcoin can only be spent by presenting the corresponding private key signature and public key hash. Okay, Bitcoin addresses that begin with 3 are pay-to-script hash addresses, sometimes erroneously called multi-signature or multi-sig addresses. I mentioned you before because you can generate different pay-to-script hash transactions. And as an example, I will give you a SHA-1 collision pay-to-script hash transaction. They designate the beneficiary of a Bitcoin transaction as the hash of a script instead of the owner of a public key. The feature was introduced in January 2012 with BECH32. Unlike pay-to-public key hash, funds sent to 3 addresses require something more than the presentation of 1 public key hash and 1 private key signature as proof of ownership. The requirements are designated at the time the address is created within the script. And all inputs to this address will be encumbered with the same requirements. So the address is actually created with the script. So if you mistype the address, then you need to find a script that will hash to it, right? So this means that you have to solve the pre-image resistance of double SHA-256, which will be very hard, or RIPE-MD. So a pay-to-script hash address is created from a transaction script which defines who can spend the transaction output. Encoding a pay-to-script hash address involves using the same double hash function as used during the creation of a Bitcoin address, only applied on the script instead of the public key hash. So the difference is that we had the K here, which was your public key, which was a point on the elliptic curve. This time we put script here, okay? So this is why in order to get the script, you have to solve the pre-image resistance of both the RIPE-MD and SHA-256. The resulting script hash is encoded with base 58 with a version prefix of 5, which results in an encoded address starting with 3. Okay, so here's an example where the hidden message was included. I mentioned before. So, okay, actually, maybe order of the slides are kind of mistaken here, but I will continue anyway. So here I told you that there was a transaction that sent money to Bitcoin address that starts with God and Bible. In this transaction, as you can see, it actually contains 3 transactions. One of them starting with the index 0 to this. One is this, and there's also another transaction. Actually, there's no address it sends, and the script starts with op return. I mentioned you this before. When it says op return, it returns true. So actually miners do not care what is written below it because the software says exists checking the block, sorry, transaction. So you can actually hide the message below it to here. Okay. So if you take this hexadecimal value, put it on a hexadecimal reader, you realize that there is a text here. It is a quotation from Bible. Okay. So this way you can hide messages in blockchain. Okay. So next thing is to BECH32 addresses. BECH32 is a SegWit address format specified by BIP 173 and is more efficient with block space. A BECH address is created from a public key as follows. Having a compressed public key, starting with 2 or 3, followed by 32 byte X coordinate. So here, as an example, it starts with 0, 2, and this is the X coordinate. I told you before, once you have an X coordinate, most of the time you get, 2 points with 2 different Y coordinates, and one of them is odd and one of them is even. So here, when you say 0, 2, actually, as far as I know, you take the odd numbered Y coordinates. When it is 3, you get the even Y coordinates. You perform SHA-256 hashing on the public key. This is the hash output. Then you perform RIPE-MD. This is the output of RIPE-MD, which is shorter. The result of step 3 is an array of 8-bit unsigned integers. And BECH32 encoding converts this to an array of 5-bit unsigned integers. So we squash the bytes to get in hexadecimal this, in numbers as this, but as 5 bits binary, this is what you get. You add the witness version byte in front of the step 4 result. Current version is 0. Okay, so to this hexadecimal value, you add 0 byte here. You compute the checksum by using the data from step 5 and the human readable part. Human readable part is just BC1, by the way. So this is the checksum. So you add it in to the end, append the checksum to the result of step 5. We now have an array of 5-bit integers. Map each value to its corresponding character in BECH32. So there are only 32 characters in this encoding, which is very small. In base 58, we had 58 characters. Now we have shorter space. So the mapping is as follows, 0, 0 is mapped to Q, 0E mapped to W, and so on. So you start mapping these two characters in BECH32 alphabet. Then you put BC1 to the beginning. This is the human readable. With this, you understand that this is BECH32 address, which is a result of, SegWit software. Soft fork. The address starts with BC1 and are typically 42 characters long rather than 34 characters of the traditional Bitcoin addresses starting with 1. Since we are now using a smaller encoding space, the length of the address is longer, but it is now harder to mistype anything because the character space is somewhat smaller. Okay.